To calculate the transformer size for the specified loads, we'll determine the apparent power in volt-amperes for each load and then sum these values to find the total volt-amperes required. Firstly, let's calculate the apparent power for the 150 amps, one-phase, 110 volts load. The formula for apparent power in a single-phase circuit is volt-amperes equals voltage times current. Therefore, the volt-amperes for this load is 110 volts multiplied by 150 amps, which equals 16,500 volt-amperes. Secondly, we'll calculate the apparent power for the 1000 amps, one-phase 220 volts load. Using the same formula, the volt-amperes for this load is 220 volts multiplied by 1000 amps, which equals 220,000 volt-amperes. Thirdly, let's calculate the apparent power for the 150 amps, three-phase, 380 volts load. For a three-phase load, we first calculate the volt-amperes per phase. The formula is volt-amperes per phase equals voltage times current. In this case, it's 380 volts multiplied by 150 amps, which equals 57,000 volt-amperes per phase. To find the total volt-amperes for the three-phase load, we multiply the volt-amperes per phase by the number of phases, which is 3. Therefore, the total volt-amperes for this load is 57,000 volt-amperes per phase multiplied by 3, which equals 171,000 volt-amperes. Fourthly, we'll calculate the apparent power for the 300 amps, three-phase, 220 volts load. Again, we start by calculating the volt-amperes per phase, which is 220 volts multiplied by 300 amps, equaling 66,000 volt-amperes per phase. To find the total volt-amperes for this three-phase load, we multiply the volt-amperes per phase by 3. Therefore, the total volt-amperes for this load is 66,000 volt-amperes per phase multiplied by 3, which equals 198,000 volt-amperes. To determine the total transformer size, we sum the volt-amperes ratings of all the loads. So, we add 16,500 volt-amperes, 220,000 volt-amperes, 171,000 volt-amperes, and 198,000 volt-amperes. The total volt-amperes is 605,500 volt-amperes. Therefore, the required transformer size is 605,500 volt-amperes. When selecting a transformer, it is important to consider several factors beyond just the calculated volt-ampere rating. One such factor is the power factor of the loads. The power factor represents the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt-amperes. Loads with a lower power factor require a larger transformer to deliver the same amount of real power. If the power factor of the loads is significantly less than 1, the transformer size may need to be increased accordingly. Another important consideration is the anticipated load growth. It is generally advisable to select a transformer with some extra capacity to accommodate future increases in load. This can help avoid the need to replace the transformer prematurely if the load grows beyond its initial rating. A common practice is to add a safety margin of 20 to 25% to calculated transformer size to account for future load growth. Additionally, the operating environment can affect the transformer's performance. High ambient temperatures or poor ventilation can reduce the transformer's capacity and lifespan. If the transformer is to be installed in a harsh environment, it may be necessary to select a larger transformer or provide additional cooling to ensure reliable operation. The transformer's impedance is another important parameter to consider. The impedance affects the voltage regulation of the transformer and the fault current levels in the electrical system. A transformer with a lower impedance will provide better voltage regulation but will also result in higher fault current levels. Conversely, a transformer with a higher impedance will have poor voltage regulation but lower fault current levels. The appropriate impedance level should be selected based on the specific requirements of the application. Furthermore, the transformer's efficiency should be considered. A more efficient transformer will waste less energy in the form of heat, resulting in lower operating costs. While more efficient transformers may have a higher initial cost, the savings in energy cost over the transformer's lifespan can often outweigh the initial investment. The transformer's voltage rating must also be compatible with the source voltage and the load voltage. In this case, the source voltage is 380 volts, 3-phase, 4-wire, and the loads operate at 110 volts, 220 volts, and 380 volts. The transformer must be able to step down the 380 volt source voltage to the required load voltages. In addition to these technical considerations, there are also several practical factors to consider when selecting a transformer. These include the available space for the transformer, the weight of the transformer, and the accessibility for maintenance. The transformer should be installed in a location that is well ventilated and protected from the elements. It should also be easily accessible for routine maintenance and repairs. Finally, it is important to comply with all applicable electrical codes and standards when selecting and installing a transformer. These codes and standards provide guidance on the safe and reliable installation of electrical equipment. In the United States, the National Electrical Code, also known as NEC, provides comprehensive requirements for electrical installations. For example, NEC Section 450.3 provides requirements for transformer overcurrent protection, and NEC Section 450.13 provides requirements for transformer disconnecting means. The calculated transformer size of 605,500 volt-amperes represents the minimum required capacity to supply the specified loads. However, it is important to consider all of the factors mentioned above to ensure that the selected transformer is appropriate for the application and will provide reliable and safe operation. Let's delve a bit deeper into the practical implications of selecting a transformer based on these calculations, and how it ties into real-world applications and safety standards. When we arrived at a total of 605,500 volt-amperes, this figure represents the apparent power demand of all the connected loads. However, transformers are typically rated in kilovolt-amperes, or kV, which is simply volt-amperes divided by 1000. So 605,500 volt-amperes translates to 605.5 kVA. In practical scenarios, transformers are available in standard sizes, and it's unlikely that you'll find one rated exactly at 605.5 kVA. Therefore, you would typically select the next largest standard size, which might be a 625 kVA or even 750 kVA transformer, depending on the manufacturer's offerings and local availability. Now let's discuss the importance of considering the power factor. As mentioned earlier, the power factor is the ratio of real power to apparent power. Ideal power factor is 1, indicating that all the apparent power is being used as real power to perform work. However, many loads, especially inductive loads like motors and fluorescent lighting, have power factors less than 1. This means that the transformer must supply more apparent power than the actual real power being consumed. If the loads in this scenario have a combined power factor of, say, 0.8, then the required kVA of the transformer would be higher than 605.5 kVA. To calculate the required kVA with a power factor of 0.8, you would divide the total real power requirement by the power factor. Assuming the 605.5 kVA is the apparent power, you would need to know the real power in kilowatts to properly adjust the calculation. If we assume that the real power is 605.5 kVA multiplied by 0.8, resulting in 484.4 kilowatts, then the required kVA would still be 605.5 kVA. This is because the initial calculation was based on apparent power. However, if you knew the real power requirement was 605.5 kilowatts, then you would divide 605.5 kilowatts by 0.8, resulting in a required apparent power of 756.875 kVA. This example demonstrates how a lower power factor necessitates a larger transformer. Another crucial aspect is the transformer's cooling method. Transformers generate heat due to core losses and copper losses. This heat must be dissipated to prevent overheating, which can damage the transformer. Common cooling methods include air natural, air forced, oil natural, and oil forced. Air natural cooling relies on natural convection to dissipate heat, while air forced cooling uses fans to increase airflow. Oil natural cooling uses oil as a coolant, relying on natural convection within the oil, and oil forced cooling uses pumps to circulate the oil. The choice of cooling method depends on the transformer's size, the ambient temperature, and the load profile. Larger transformers typically require oil cooling due to their higher heat generation. The NEC and other electrical codes provide guidelines on transformer installation, including clearances, ventilation, and grounding. For instance, NEC section 450.21 specifies ventilation requirements for transformers, and NEC section 250 provides detailed requirements for grounding transformers. Proper grounding is essential for safety, as it provides a path for fault current to flow, allowing overcurrent protective devices to trip and clear the fault. Overcurrent protection, such as fuses or circuit breakers, is also crucial for protecting the transformer from overload and short circuits. NEC section 450.3 specifies the overcurrent protection requirements for transformers, which vary depending on the transformer size and voltage. Furthermore, transformers should be installed in a location that is accessible for maintenance and inspection. Clearances around the transformer must be maintained to allow for safe working conditions. Regular maintenance, such as inspecting oil levels, checking for leaks, and testing insulation resistance, is essential for ensuring the transformer's reliability and longevity. In addition to the NEC, other standards, such as those published by the Institute of Electrical and Electronics Engineers, also known as IEE, provide guidance on transformer selection, installation, and maintenance. For example, IEE Standard C57.12 covers general requirements for liquid immersed distribution, power, and regulating transformers. Let's also talk about the impact of transformer impedance on system performance. Transformer impedance is expressed as a percentage of the transformer's kVA rating and represents the opposition to current flow within the transformer. A lower impedance transformer will have a higher fault current and better voltage regulation, while a higher impedance transformer will have a lower fault current and poor voltage regulation. The choice of impedance depends on the specific application and the coordination of overcurrent protective devices. If the transformer is feeding a large motor load, a lower impedance transformer may be desirable to provide better voltage regulation during motor starting. However, a lower impedance transformer will also result in higher fault currents, which must be considered when selecting overcurrent protective devices. Conversely, if the transformer is feeding a sensitive electronic load, a higher impedance transformer may be desirable to reduce fault current levels and protect the electronic equipment. In summary, selecting the right transformer involves a comprehensive analysis of the load requirements, power factor, operating environment, cooling method, impedance, and applicable codes and standards. The calculation of the total volt-amperes is just the first step in this process. It is crucial to consider all of these factors to ensure that the selected transformer is appropriate for the application and will provide reliable, safe, and efficient operation. Remember that working with electrical systems can be dangerous, and it is always recommended to consult with a qualified electrical engineer or electrician when selecting and installing transformers. These professionals have the knowledge and experience to ensure that the installation is done safely and in compliance with all applicable codes and standards. Furthermore, it is always a good practice to document all calculations and decisions made during the transformer selection process. This documentation can be helpful for future maintenance and troubleshooting. It is also important to keep accurate records of the transformer's nameplate data, including the kVA rating, voltage rating, impedance, and cooling method. This information will be needed for future reference and maintenance. By following these guidelines and consulting with qualified professionals, you can ensure that your transformer is properly sized and installed for your specific application.